So now we are going to have some introduction and history chapter, and that chapter I recommend you to watch next subject movie about the project from which Dpi had started in 1960s, and later you will find out that Dpi was not concentrated on oil research at the beginning. Firstly, it was Mohole scientific project, which was engaged in sampling of the Earth's seabed in the middle of the ocean, and the main task was to prove the Andrea Mohorovich's theory about construction of the Earth as a planet.
Man's knowledge of the Earth is a little like an ant on the surface of an apple who wants to understand the apple but cannot penetrate its skin. The skin of an apple, proportionately, is about as thick as the crust of the Earth. A scientific project is underway, a project called Project Mohole, which hopes one day to drill a hole through the crust of the Earth and to find out what's down there. Since it is thought that the crust of the Earth is thinnest at points under the ocean depths, it is probable that the drilling will take place at some point deep under the ocean.
The hole to the interior of the lakes developed by the petroleum industry in its search for oil. The Mohole drill must go at least a mile deeper than the deepest hole ever drilled on land, and the special problems of drilling at sea will make the task much more difficult. But sea-going rigs like this have already shown the way. This ship, the Cuss-1, with its 98-foot derrick, is a former naval vessel converted for offshore drilling. Here in the shallow waters of the Pacific Ocean off California, her drill teams are probing for oil, going about a mile deep into the ocean bottom below. To adapt equipment like this to the dramatic task of penetrating the very crust of the Earth is a major operation. The drilling ship will have to be held in position above the hole in water over 2 miles deep, through long periods of time, night and day, in fair weather and foul. The miles of drill pipe must be able to resist the wrenching forces of the ocean currents. There are many other hazards and problems. But the planners of Project Mohole, intent on finding out what's down there under the sea, believe that the obstacles can and will be overcome. The effort is going forward on several fronts at once. While one group of the scores of scientists involved studies the technical problems of drilling at sea, other groups are studying the ocean bottom at sites in both the Pacific and the Atlantic Oceans. The first oceanographic survey to help find the place where the hole may be drilled takes place in the Atlantic. 200 miles north of the island of Puerto Rico, scientists hope to find that the crust of the Earth beneath the sea is thin enough to be pierced by the proposed drilling equipment. Under the continents, and even under an island like Puerto Rico, the crust of the Earth is from 20 to 30 miles thick, but underneath the ocean, the crust may be as thin as 4 miles. The first layer is composed of soft sediments. Beneath that is dense, hard rock. Between this crust and the Earth's mantle is the Mohole, the boundary between the crust and mantle, named for the Yugoslav scientist Mohorovic who discovered it. No one knows much about the mysterious Mohole, and no one knows for certain what the mantle is made of. Now in the blue water off Puerto Rico, the research vessel Vima sails over the Puerto Rican Trench. The Vima, a schooner specially equipped for oceanographic research, is staffed by scientists of the Lamont Geological Observatory of Columbia University. She is the leader of a 4-ship expedition in search of Mohole. It's a rugged, active life aboard the Vima. That's Dr. John Nape, Scientific Director, in the rigging. Precision depth recordings, measuring the landscape far below, are made constantly as the Vima plows through the waves. By sending sonar signals down to the bottom at precise intervals and recording the echo of each signal as it returns to the ship, the precision depth recorder traces a profile of the ocean floor. Each ping of the echo sounder adds another point to the picture of the ocean floor far below the passing ship. Hidden in the darkness of the sea, the bottom of the ocean is as varied as the surface of the continents, and on an even more majestic scale. It has gorges rivaling the Grand Canyon, mountains taller than Everest, plains as vast as the Russian steppes. Underneath the oceans flooding half our world, drowned in eternal cold and darkness, is a land that conceals more mysteries than the moon. To obtain a sample of the uppermost layer of the ocean floor, the Vima heaves to north of the Puerto Rican Trench. Sails come down and the scientists make ready for the delicate, strenuous coring operation. The 30-foot-long piston coring pipe is in its rack along the rail. About 3 inches in diameter, the steel pipe has a sharp cutting edge at its bottom end for piercing through the ocean floor. The pipe is released and lowered into the water. At its top end, the pipe is equipped with a heavy lead weight and triggering mechanism to plunge the coring pipe into the bottom. Miles of cable unroll from the powerful winch amidships on the Vima, lowering the core through the sea. The echo sounder reflects the beginning of the descent, drawing a picture of a slender finger of steel as it probes the unknown. On deck, there's a 2-hour wait for the corer to reach bottom. What kind of bottom will we find? Will the corer hit rock, or will it drive deep into the ocean floor to bring up new evidence of the Earth's history? The scientists gather around the tension indicator that will tell them when the pipe hits. The hit is made. The corer plunges into the bottom. Now the winch winds in the cable with the coring pipe and its precious load. It took only seconds to drive its way into the bottom, but in those seconds it may have pierced through layers of sediment laid down over millions of years. The coring pipe finally reaches the surface. What will this sample reveal about this part of the ocean as a possible site for drilling the Mohole? The core barrel is hoisted into its rack along the rail. The fins and lead weight are removed. There's the end of the core in the barrel. The mud that still clings to the outside of the pipe offers the scientists the first clues to what's inside. Now the core is extruded. As the pipe is pulled along the trough, the piston inside pushes the core out. A section of the floor of the Atlantic, punched out of layers of sediments miles below, is clearly exposed to view on the deck of the Vima. Dr. Charles Drake examines the core. Scraping off small samples at intervals along the core, he makes a preliminary inspection of its contents. He files the samples temporarily on his arm. The sections of the core are stowed below. Dr. Drake tests a sample of the core between his teeth. It seems gritty. This suggests the remains of microscopic shells and skeletons which may form a record of centuries of deep-sea life. This core represents 30 feet of sediments and reaches back about 9 million years. The first step of the Mohole project is to core completely through the sediments, through hundreds of millions of years. In the Lamont laboratories, the cores will be split open and analyzed. The color, content, and composition of the split open cores are clues to the history of the world. Sometimes the opened-up core reveals clearly distinguished layers of sediment. Each layer may have been laid down in 1 year or in 5,000 years, a timetable to be read by the skilled interpreter. At present, such cores are the only direct method of studying the bottom. Knowledge of the deeper layers rests on indirect methods, such as seismic recordings. Just as the pings of the depth recorder can produce profile pictures of the ocean floor, so it is possible with the much greater sound energy of underwater explosions to measure the thickness of the layers of rock beneath the floor. The 4 ships of the expedition now work as a team in making seismic recordings. From the Vima, Dr. Naif radios the day's instructions.
The ship's in order, south to north. Bear on 21:36 minutes north.
The research vessel Bear is from Woods Hole Oceanographic Institution. The Hidalgo from Texas A&M University. And from Columbia's Hudson Laboratories comes the Gibbs. The Vima hoists signals. While one ship sets off underwater explosions, the other ships will listen. On this run, the Vima, Bear, and Hidalgo will take listening positions in a line 30 miles apart, while the Gibbs makes the firing run. Following a carefully plotted course, the Gibbs gets underway to drop high explosives into the sea. For listening, the Vima goes on silent ship. Auxiliary engines and generators are shut off. Scientists break out the hydrophones, supersensitive microphones encased in rubber, and lower them into the sea to pick up the distant explosions. The Vima's geophysical camera is ready and waiting to record the shots. Dr. Naif slacks the cable so the hydrophones will be floating free. Just before the shot, the camera is switched on. The sound of the explosion goes through the water and into the earth below. Sound waves travel faster in the deeper, more rigid layers. Even though the distance is greater, the sound waves traveling past the Mohole arrive at the listening ship first. Waves from the upper layers arrive later. Dr. Naif hauls in the hydrophones at the end of this round of firing, and the Vima scientists wait for the photographic record to be developed. The seismic record, still wet, is spread out for inspection. Comparing the speeds of these waves, oceanographers can determine the thickness of the layers of the Earth's crust. Ground wave 1 traveled beneath the Mohole and ground wave 2 through the deep crust. comparison of these fast waves can reveal the depth to the Mohole. Far over on the record is the slow ground wave 3, which traveled in the top sedimentary layer. Many such records, analyzed in detail, can produce a comprehensive picture of the structure of the Earth's crust. Now it's the Vima's turn to do the firing. She sails down the line of listening ships in a heavy sea to fire repeated shots that will help fill in the seismic records of this part of the Atlantic. Her auxiliary engines are set at full speed. A firing ship moves fast to escape from her own shots and to get in as many of them as possible in one day. The Vima is carrying 10 tons of high explosives. From 3-pounders up to regulation 300-pound Navy depth charges, they're ready on deck.
Hello, Gibbs. This is Vima. This is shot number 357, a Mark 8 300-pound charge. 6-foot fuse, burning time about 90 seconds. Your 1-minute warning, now. 5, 4, 3, 2, 1, 0. Over the side. The charge is over the side.
The more rigid the layer, the faster sound travels. The fastest waves go past the Mohole and back to reach the listening ship.
5, 4, 3, 2, 1, 0. Over the side. The charge is over the side. Hello, Bear. This is Vima. This is shot 415. Over the side. The charge is over the side.
The firing goes on into the night. The expedition scientists want every minute at sea to count. The opportunity for gathering scientific evidence of many different kinds is a priceless one. As the day's firing ends at last, the scientists of the Vima meet on the afterdeck to plan the next day's work. Here off Puerto Rico is one possible site for drilling the Mohole. The full interpretation of all the information gathered will take time. But in this preliminary survey stage, much has already been learned. The seagoing rig that will one day drill through the Mohole will add new direct evidence to our knowledge of the Earth. Somewhere down there, the drill may pass through the time and place of life's beginning. Down there is the record of the birth of our planet. And somewhere down there, perhaps, great unexpected discoveries are waiting to be made by the scientists, engineers, and technicians of Project Mohole.
Now I would like to share with you some industry interesting facts which shows us in details how the developing of the industry happened till the present time. So starting from 1961. In 1961, the first automatic DP operations from the drilling vessel Erika happened, and we watched already the subject movie about Mohole project when Erika actually started in the industry as DP project. Then very fast in 1962, French introduced pipe-lay vessel Salvor and Terrible in Mediterranean Sea. After a few years, in 1964, it was the introduction of the drilling vessel known as a coal drill, and that coal drill had automatically operated thrusters, which actually also may be called as the first Dpi project. In 1974, United Kingdom entered with a GEC system for drill ship WinPC Lab, and that ship been constructed already for deep water core sampling. But by the way, the term deep water with the years very changeable. Let's say half a century ago, deep water means the depth higher than 70 meters. Today, IMCA says that deep water is a depth which higher than 600 meters. So 670 meters, let's say, huge improvement we have. In 1977, semi-submersible platform Uncle John was developed and presented on the market. At the same year, Kongsberg in Norway developed the Dpi vessel known as a Seaway Eagle. And some statistic. In 1980, the number of Dpi capable vessels totaled about 65. And then in 1985, general amount of Dpi vessels had increased to about 150 pieces. After that, in 1986, generally we have the value 100 plus Dpi capable vessels which were operational worldwide, so which been in Dpi activities. In 1999 it was over 500, and in 2006 industry already claimed that they had about 2,500 vessels which are capable to work on Dpi. The amount of Dpi vessels, of course, is not a stable parameter, and if we have a peak of offshore activities, then the number of the vessels increased. Generally saying, today we have about 5,000 Dpi capable vessels worldwide, and this is just more or less about 3% of global fleet in the world. So think about that. And here is the answer for the question why it is so hard to find your first experience and to find your first, let's say, Dpi vessel, which is in Dpi chart, especially right now, because everyone knows that today, I mean 2019, 2020, offshore industry has actually a crisis. So some summary of interesting facts. As I said to you before, nowadays we have 5,000 Dpi capable vessels which are out there, and that number is still expanding. But 5,000 Dpi capable vessels, this phrase means that we have just what? 3% of global fleet which is fitted with Dpi system. Also, it could be said that today Dpi comes as a standard for certain type of operations at sea due to operational safety which may provide the Dpi concept. The main idea of Dpi to increase the operational safety but not to improve the accuracy of station keeping, remember that. Many vessels coming into service are Dpi capable to some level, whether the vessel is going to use it or no. And Will the vessel use it or no depends on charter requirements and all operational risks which assessed in advance and which may be significantly increased due to loss of position by the vessel which engaged in charter. And now, colleagues, is the right time to give the dynamic positioning system definition. And I would like you to know the first source of information, where are the requirements and regulations are provided. So, first of all, we always refer to STCW, section B 5/F. It is known as a guidance on the training and experience for personnel operating dynamic positioning. And here we have the main definition about what is DP. DP means dynamic positioning, and it is defined as a system whereby a self-propelled vessel's position and heading is automatically controlled by using its own propulsion units. That's all. Or in other words, DP is a system which controls automatically heading and position under desired excursions with the means of only active thrust. That's one version more, if you like.